Good morning, my name is Engineer Martin Plaza and this is Parasitic capacitant. Electric current. An electric current is a flow of electric charge. The SI unit for measuring an electric current is the ampere, which is the flow of electric charge across a surface at the rate of 1 coulomb per second. Electric current is measured using a device called a ammeter. All actual circuit elements such as inductors, diodes and transistors have internal capacitance, which can cause their behavior to depart from that of ideal circuit element.
Hi and welcome to the 2-Minute Guru. My name is Daniel Bogdanoff. Stick around to find out why electrical current gets on my nerves. Literally. Electrical current is simply the flow of charge through space, and we measure that in amperes or amps. In electronics, we're typically talking about the flow of electrons and typically through a wire, but in semiconductor physics, we can talk about the flow of holes, which is essentially how a bipolar junction transistor works. And in biology or chemistry, we can talk about the flow of ions, which is essentially how your nerves work. And you've probably heard it said that electricity takes the path of least resistance. And this is true, but it can be a little bit misleading. Just like a river will fork around an island, electricity can take multiple paths depending on what it's encountering. To take that analogy a little further, I've poked some different sized holes in the lid of this water bottle. Now, obviously, current is going to flow out of both holes, not just the bigger one. Let's take a look. And I'll say that the holes in this water bottle are akin to resistors in your circuit. Now, notice that a lot more water came out of the bigger hole, and obviously there's a lot more water in this glass than in this little glass. This is a lot like how current flows through resistors. More electricity is going to go through the smaller resistor, the bigger hole, remember the straw analogy from earlier, and less current is going to flow through the little hole. And it's actually going to be proportional to the size of the holes or to the values of the resistors. So we can see that electricity does take the path of least resistance, just not exclusively. Let's look at an actual example. I have the function generator of my scope outputting a 10-volt peak-to-peak sine wave, and if I take my clamp-on current meter, we can see how much current is flowing through this 200-ohm resistor. And if I look at my measurement, I'm seeing about 46 milliamps of current flowing through this resistor. I should also point out I'm in averaging acquisition mode because clamp-on current probes are notoriously noisy. If you don't know what that means, check out my video in season 1 where I talk about acquisition modes. Now let's see what happens to the current if I keep the voltage the same but add another resistor. Now I've added an identical resistor in parallel, so current is going to flow equally through both of them. And if I look at my measurements, I'm now seeing about 73 milliamps of current. So you can see that if I half the resistance by putting two resistors in parallel, like we talked about in the last video, and provide the same voltage, I'm actually getting twice as much current flowing through these resistors. So you can think of current and resistance like your sink faucet. There's consistent water pressure from the mains, but because the resistance of your sink, the choke valve, is so tight, no current, no water is getting through. As you start to open that up or lower your resistance, you're going to get more and more current going through your sink. That's all we have time for today. Make sure you subscribe to the Keysight Oscilloscope's YouTube channel so you can see when the next episode comes out. We're going to be talking about voltage. Thanks for watching. If you have any topics that you want me to cover, please put them in the comments. I'm Daniel Bogdanoff, and I'll see you next time.
Resistivity. All conductive materials such as metal have some inherent ability to oppose the flow of electric current, known as resistivity. It is represented by uppercase letter R. The standard unit of resistance is the ohm, sometimes written out as a word and sometimes symbolized by the uppercase Greek letter omega.
Resistance and conductance are more than just fundamental electrical characteristics. They're the backbone of why our electrical circuits work today. Hi and welcome to the 2-Minute Guru. My name is Daniel Bogdanoff, and today we're going to talk about resistance and conductance. Resistance we measure in ohms, and conductance we measure in Siemens, and they're actually inversely proportional to each other. So an interesting side note is that 1 ohm actually equals 1 Siemens. Most of the materials we use in electrical engineering are either going to be highly conductive, like a wire, and we call those conductors, or they're going to be highly resistive, like, well, a resistor, and we call them insulators. Because air is highly resistive, it's a good insulator, and wire is highly conductive, it's a good conductor, we can create electrical circuits to control the flow of electricity. Let's take a closer look at what resistance is. Like most electrical characteristics, it really helps to think about them in terms of analogies that work for you. So make sure you find an analogy that works for you for each of the different electrical characteristics. This is the one I like to think of when I think about resistance. Resistance is a lot like drinking straws. Have you ever tried to drink out of one of these little stir straws? You have to work pretty hard just to get a little bit of your drink. That's like having high resistance. And then if you have a bigger straw, it's a lot easier to get your drink out. That's like having a lower resistance. You don't have to work as hard to get the same amount of liquid flow. So let's take a look at an example. I have a resistor hooked up to my power supply, supplying a constant 5 milliamps of current, and we're going to see how much work my power supply has to do, how much voltage it's going to apply to get 5 milliamps of current through this resistor. And if I look at this, it looks like it's about 1.1 volt to get 5 milliamps through this resistor. Voltage, current, and resistance all behave according to Ohm's law, which we will cover in a later video. Another interesting side note is that the unit of conductance is named after Werner von Siemens, who founded a company by the same name. He is the one who established that electricity could be used as a power source. He invented the first elevator, he invented the trolley bus or the trolley, and he invented the electromechanical dynamic transducer, better known as a speaker. That's all we have time for today. Next time we're going to talk about how to combine resistances. So make sure you subscribe to the Keysight Oscilloscope's YouTube channel. The next few episodes are going to cover some double E basics, and then we're going to go on to learn how those apply to us in the lab every day. Thanks for watching. My name is Daniel Bogdanoff, and I'll be back with a new 2-Minute Guru video every other week.
Capacitance. Capacitance is the ratio of the change in an electric charge in a system to corresponding change in its electrical potential. Two parallel plates will always have some capacitance between them.
Today we're going to use an oscilloscope to look at the 3 different effects that capacitance can have on electrical systems. Hi, welcome to the 2-Minute Guru. My name is Daniel Bogdanoff. Earlier in this season, we've been looking pretty much at DC systems. We've looked at resistance, voltage, and current. Now it's time to look at AC systems, and today we're going to look at capacitance. We're going to look at the 3 effects that capacitors have on your system using an actual capacitor, but capacitance is actually present in pretty much every electrical system, so understanding what those 3 effects are will help you analyze and diagnose your circuits later on. Our circuit setup today is super simple. We have the wavegen from my oscilloscope running through a resistor, and that's probed with channel 1, and then we're going to put a capacitor in parallel with that resistor to see what happens. The first effect that capacitance has on a system is it's going to resist a change in voltage and store charge, according to the formula Q equals C times V. So let's add the capacitor and compare before and after. I'm going to save this waveform using a reference waveform. So I hit the reference waveform, save to R1, and then I'm going to display it on screen. So when I turn off channel 1, you can actually see that waveform there. Now let's turn channel 1 back on and add the capacitor. And you can see if I zoom in here, this region, my capacitor is charging up. It's resisting that step up in voltage. Here my capacitor is starting to discharge, so all of that charge stored up when the voltage was high is slowly trickling out of my capacitor after my source voltage has already gone low. So if you see your system resisting voltage changes or adding some charge back in after the voltage has turned off, you know that's a capacitive effect. And this effect is roughly how switch mode power supplies operate. When the power is supplied to the capacitor, it begins to charge up, and then when it's turned off, the capacitor discharges that energy into the system. And that leads us to the second effect of capacitance, frequency filtering. There's two different ways to look at this. First, let's look at our signal from before. Remember that a square wave is made up of an infinite number of increasing frequency sine waves. When I remove the capacitor, we get a nice crisp edge, but when I add the capacitor, we see that that edge gets a little rounder, and that's because the capacitor is filtering out the higher frequency components that make up that nice square wave. And that's all we have time for this week. We're going to pick it back up next episode when we look at frequency filtering on a pure sine wave and the third effect that capacitance has on your electrical systems. Thanks for watching. Make sure you subscribe to the Keysight Oscilloscopes YouTube channel. We have new videos every week. And make sure you download the new ebook, 6 Essential Tips for Getting the Most Out of Your Oscilloscope.
Inductance. Inductance is a property of an electrical conductor which opposes a change in current. Mutual inductance describes the change of current in a circuit when a second circuit also experiences of a change of current. Energy is coupled from one circuit to the other through magnetic field. It does that by storing and releasing energy from a magnetic field surrounding the conductor when current flows, according to Faraday's law to induction.
Last episode, we looked at how capacitance can affect your electronics. In this episode, we're going to look at the 3 different effects that inductance can have on your circuits. Hi, and welcome to the 2-Minute Guru. My name is Daniel Bogdanoff, and today we're going to use an oscilloscope to look at the 3 different effects that an inductor can have in an electronic circuit. The first effect of inductance is that it stores energy in the form of a magnetic field. So to look at that, we have my oscilloscope piping out a square wave from my function generator through a resistor, and we're going to add an inductor in series to see how that changes my signal. So with our series inductor, you can see these spikes show up on the oscilloscope screen. And what's happening is when the signal is low, the inductor is charging up, and as soon as the signal switches high, it's pushing that energy back into the system, and that turns up as a spike on the screen. The second effect of inductance is that it filters out frequency. It's going to filter out the high frequency signals and let the low signals pass through it as if it were a wire. So for the higher frequency components of my square wave input, we can see that the inductor is actively working against that change, but over time the inductor is going to charge up all the way and more or less act as a short circuit. The third effect of inductance is that it changes the phase relationship between voltage and current. And if we look at my oscilloscope, channel 1 is my voltage, channel 2 is my current, and you can see my oscilloscope is measuring a roughly 20-degree difference between voltage and current. In an ideal world, it should be 0 degrees because I'm just measuring a resistor, but there's some built-in parasitic inductance and capacitance in my circuit. To learn more, check out the video Identifying Parasitic Inductance. There's a card for that, and there's a link for it in the description. We talk about the built-in inductance in this type of setup, and also the step response of inductors and capacitors in an AC world. So let's look at what happens when I include my inductor in my circuit. We're going to see a pretty significant phase relationship change between voltage and current. And we can see that my voltage is now leading my current. I see a 90-degree phase shift measured on my oscilloscope, and I can tell that my voltage is leading because the rising edge of my voltage happens earlier in time than the rising edge of my current. So my current is lagging or my voltage is leading. That's all for today. Thanks for watching. If you liked this video, hit the thumbs up button. And if you haven't already, subscribe to the Keysight Oscilloscopes YouTube channel. And if you want to get better at using oscilloscopes, download the free ebook, 6 Essential Tips for Getting the Most Out of Your Oscilloscope. I'm Daniel Bogdanoff, and I will see you next time.
Parasitic capacitance. The parasitic capacitance or strike capacitance is an unavoidable and usually unwanted capacitance that exist between the parts of an electronic component or circuit simply because of their proximity to each other. When two electrical conductors at different voltage are close together, the electric fields between them cause electric charge to be stored on them. This effect is parasitic capacitance. The parasitic capacitance between the term of an inductor or other wound component is often described as self-capacitance. However, self-capacitance of a conductive object is a different phenomenon, referring to the capacitance of the object without reference to another object.
In most of our discussions so far, we've assumed that all our circuits are perfect, that all the resistors, capacitors and inductors have the values which we've picked, and that we've placed them in exactly the places we'd like them to go. However, in reality, any two wires have a capacitance between them, even if it's very small, because they act like the two plates of a capacitor. Wires also obviously have a resistance, and perhaps less obviously have an inductance, because each wire is like a single turn of an inductor. These components, which are part of the very fabric of our wires and conductors, are called distributed components. Because the values of these components are generally very small, they usually only affect the circuit at high frequencies. However, at such high frequencies, they can be a problem and are called parasitic components. We can draw on representations of these onto a generalized block diagram, as shown on the screen. Parasitics have two bad effects on the circuit. Firstly, unwanted signals can get into places where they shouldn't be, because they can pass through the parasitic capacitances or through the magnetic fields of the parasitic inductors. Secondly, they mean that all circuits will be limited in their frequency of operation because they contain low-pass filters, as shown in the diagram, and stop working at high frequencies. And also, because these are filters, they can exhibit unexpected phase changes at these frequencies. You should also note that although we've just been discussing input and output wires, parasitics exist internally among all the wires within the block. And there are even very small resistances between wires because there's no such thing as a perfect insulator between them. Parasitics are one reason, but not the only reason, why designing circuits to operate at higher frequencies is a more challenging task than designing them to operate at lower ones.
Thank you.